Essay 1. On the spectrum of hydrogen. Empirical spectral laws. Hydrogen possesses not only the smallest atomic weight of all the elements, but it also occupies a peculiar position both with regard to its physical and chemical properties. One of the points where this becomes particularly apparent is the hydrogen line spectrum. The spectrum of hydrogen observed in an ordinary Geissler tube consists of a series of lines, the strongest of which lies at the red line of the spectrum, while the others extend into the ultraviolet. The distance between the various lines, as well as their intensities, constantly decreasing. In the ultraviolet, the series converges to a limit. Balmer, as we know, discovered in 1885 that it is possible to represent the wavelengths of these lines very accurately by the simple law of 1 over lambda n is equal to r times the difference of 1 over n squared from 1/4, where r is a constant and n is a whole number. The wavelengths of the 5 strongest hydrogen lines, corresponding to n equals 3, 4, 5, 6, 7, measured in air at ordinary pressure and temperature, and the values of these wavelengths multiplied by the difference of 1 over n squared from 1/4, are given in the following table. The table shows that the product is nearly constant, while the deviations are not greater than might be ascribed to experimental errors. As you already know, Balmer's discovery of the law relating to the hydrogen spectrum led to the discovery of laws applying to the spectra of other elements. The most important work in this connection was done by Rydberg in 1890 and Ritz in 1908. Rydberg pointed out that the spectra of many elements contain series of lines whose wavelengths are given approximately by the formula of 1 over lambda n is equal to a minus r over n plus alpha squared, where a and alpha are constants having different values for the various series, while r is a universal constant equal to the constant in the spectrum of hydrogen. If the wavelengths are measured in vacuo, Rydberg calculated the value of r to be 109,675. In the spectra of many elements, as opposed to the simple spectrum of hydrogen, there are several series of lines whose wavelengths are to a close approximation given by Rydberg's formula, if different values are assigned to the constants a and alpha. Rydberg showed, however, in his earliest work that certain relations existed between constants in the various series of the spectrum of one and the same element. These relations were later very successfully generalized by Ritz through the establishment of the combination principle. According to this principle, the wavelengths of the various lines in the spectrum of an element may be expressed by the formula of 1 over lambda equals fr of n1 minus fs of n2. In this formula, n1 and n2 are whole numbers, and f1 of n and f2 of n, etc. is a series of functions of n, which may be written approximately as fr of n equals r over n plus alpha r squared, where r is Rydberg's universal constant and alpha r is a constant which is different for the different functions. A particular spectral line will, according to this principle, correspond to each combination of n1 and n2 as well as to the functions f1, f2, etc. The establishment of this principle led therefore to the prediction of a great number of lines which were not included in the spectral formulae previously considered. And in a large number of cases, the calculations were found to be in close agreement with the experimental observations. In the special case of hydrogen, Ritz assumed that the formula 1 was a special case of the general formula 1 over alpha is equal to r times the difference of 1 over n2 squared from 1 over n1 squared, and therefore predicted among the other things that a series of lines in the infrared given by the formula 1 over alpha is equal to r times the difference of 1 over n squared from 1 over 9. In 1909, Paschen succeeded in observing the first two lines of this series corresponding to n equals 4 and n equals 5. The part played by hydrogen in the development of our knowledge of the spectral laws is not solely due to its ordinary simple spectrum, but it can also be traced in other less direct ways. At a time when Rydberg's laws were still in want of further consideration, Pickering in 1897 found in the spectrum of a star a series of lines whose wavelengths showed a very simple relation to the ordinary hydrogen spectrum, since to a very close approximation they could be expressed by the formula 1 over lambda is equal to r times the difference of 1 over n plus 1/2 squared from 1/4. Rydberg considered these lines to represent a new series of lines in the spectrum of hydrogen and predicted, according to his theory, the existence of still another series of hydrogen lines, the wavelengths of which would be given by 1 over lambda equals r times the difference of 1 over n squared from 1 over 3/2 squared. By examining earlier observations, it was actually found that a line had been observed in the spectrum of certain stars which coincided with the first line in this series, corresponding to n equals 2. From analogy from other spectra, it was also to be expected that this would be the strongest line. This was regarded as a great triumph for Rydberg's theory and tended to remove all doubt that the new spectrum was actually due to hydrogen. Rydberg's view has therefore been generally accepted by physicists up to the present moment. Recently, however, the question has been reopened, and Fowler in 1912 has succeeded in observing the Pickering lines in ordinary laboratory experiments. We shall return to this question again later. The discovery of these beautiful and simple laws concerning the line spectra of the elements has naturally resulted in many attempts at a theoretical explanation. Such attempts are very alluring because the simplicity of the spectral laws and the exceptional accuracy with which they apply appear to promise that the correct explanation will be very simple and will give valuable information about the properties of matter. I should like to consider some of these theories somewhat more closely, several of which are extremely interesting and have been developed with the greatest keenness and ingenuity, but unfortunately space does not permit me to do so here. I shall have to limit myself to the statement that one of the theories so far proposed appears to offer a satisfactory or even a plausible way of explaining the laws of the line spectra. Considering our deficient knowledge of the laws, which determine the processes inside atoms, it is scarcely possible to give an explanation of the kind attempted in these theories. The inadequacy of our ordinary theoretical concepts has become especially apparent from the important results which have been obtained in recent years from the theoretical and experimental study of the laws of temperature radiation. You will therefore understand that I shall not attempt to propose an explanation of the spectral laws. On the contrary, I shall try to indicate a way in which it appears possible to bring the spectral laws into close connection with other properties of the elements, which appear to be equally inexplicable on the basis of the present state of the science. In these considerations, I shall employ the results obtained from the study of temperature radiation, as well as the view of atomic structure, which has been reached by the study of the radioactive elements.